All right, everyone, let's get started. First, a very quick announcement is that I meant to have the quiz 1 due today, but I messed up and I didn't get it published in time because I intend to have a quiz every Friday unless we have an exam. And so quiz 1 is instead going to be due on Monday, but then quiz 2 will be due next Friday. So just heads up. Otherwise, let's get back to our lecture on Unit 2, multiple linear regression. Okay, so the main thing we have done last time is we derived the expressions for our beta coefficients. So we have this expression here for the intercept coefficient, and you can see it's written in terms of the sample mean for y, sample mean for x, and then the rest of the beta coefficients. And then we have an expression for the rest of the beta coefficients here in terms of the sample covariance inverse and the sample cross covariance. And also we had earlier expressions that were a little bit less interpretable, but we had this one. So this one would be, if you wanted to implement it from scratch, this is probably the easiest way to do it. You would build your A matrix like this, and then you would do this stuff. And so that's sort of the subject. Our next subject is to how we actually implement these. So let me fast forward. Okay, so here we are. So our goal now is to actually do this in Python. So as we said, one option is you construct your A matrix like this. So this is the matrix of your feature data. So along the rows, you have the samples in your data set. Along the columns, you have your different features. And so you could do this in Python with the NumPy package. You would first create a vector of ones. And this would be a vector where you have the number of samples here. So this is like you're creating this vector of ones. We'll just name it ones. And then you have to assume we've already constructed x from our data. So now we need to basically stack 1 next to x. And you can do this with the NumPy hstack, horizontal stack. And then we get our A matrix. And then we just need to solve, essentially we want to solve the y equals A beta. This is essentially, or let's say, want to approximately solve this. We want to approximately solve this problem, and we do it with least squares. So this is, you can use this least squares command in MATLAB. You could actually, okay, what I meant to say is, okay, the first thing you could do is you could do this. Now that you have the A matrix, you could like do this multiplication, you could do the matrix inverse, you could do all this stuff. And that definitely works, but there's a faster way, because whenever you do a matrix inverse, the size, the complexity grows with the cube of the dimensions. And so once these matrices get big, or in other words, if you have many features, that problem could become numerically challenging. So there's a more effective way of solving these least squares problems where you use a smart algorithm that someone has designed that solves this. Often case, it's an iterative algorithm. It goes through a number of steps. And there's many such algorithms, and you can find them programmed here in this least squares routine. So this would be, you just give it the A and the Y, and then it solves this to give you the betas. So they would give you the same exact answers, but this second scheme here would be more numerically robust and faster. Okay, so, but it turns out that we're not going to do either of these. We're going to use an even more convenient approach, which is to use the tools in this scikit-learn package, which is where we find all of our classic machine learning type things implemented. So the way that scikit-learn works is first you instantiate this model. So in this command, you sort of make like, we call this a regression object. So you make this sort of blank regression object. When you do this, it sets it up. It just, does a bunch of stuff under the hood. Once that's been made, then you can give it the data, And when you call this dot fit function, you say dot fit, you give it your data x and y. Then internally, it computes the beta according to least squares. It stores it internally. You can access it if you want, but it's stored internally. And then if you want to do something like use that for prediction, let's say I want to compute my training targets. Then I do this dot predict function. This is again the same object, this regression object. Dot predict, and then you give it your training samples here. So this is going to give you your training predictions. So notice that I've never really explicitly asked it for the beta coefficients. Those are just stored internally. Maybe I don't really care what they are. I just want to fit my model and then use it for prediction. So that's what we've done here. And then maybe you want to evaluate how good your model is. So here I'm computing this normalized RSS. So instead of using the sum here, NP sum would sum up. This is like, y hat minus y squared, element y squared. So usually if I want to compute the norm, I would sum them up. But here I'm computing the mean, so I'm summing them up and dividing by the number of samples. And then once I have that normalized RSS, I can compute r squared by dividing by the standard deviation of the targets and subtracting that from 1. And then I can print out my r squared for this problem. It turns out it's like 0.51 or 0.52. It's not that great, but whatever, that's what it is. This is the diabetes data set we're working with. Okay, so this is actually going to be how we instantiate all our classical stuff up until we get to deep learning. Then we need to do things differently. But when we do different kinds of linear models, we'll use different functions here. When we do classification, we'll use different functions here. But the framework is always the same. You instantiate this model object, then you fit the data, then you predict, you can extract weights, et cetera, et cetera. So that's what we're going to do. Any questions so far? Okay. So, and the details are in the lab, and you'll use those details to help you do. Sorry, the details are in the demo. You'll use that demo to do your next lab. But let's talk about something else that's done in the demo, which is to compare simple regression to multiple regression, because we learned two different ways of dealing with data sets. So just to review, simple regression, you have a single scalar feature, and you use that to predict the targets. Whereas in multiple linear regression, you have possibly many scalar features. Altogether, you use them to predict the target. So they become the same when D is 1 in this case. Then they're the same, but in general, here D is some number that could be larger than 1, and so they differ. So a question you might ask is, well, is multiple linear regression better? Is it always better? What do you think? Is it ever better to do simple? I think you were first.
I would say it probably depends on your data. Like if you have one thing that doesn't correlate at all, it's probably going to throw off the rest of your data, or throw off your prediction. If you have like...
Would it throw it off, or would you learn to ignore it?
Okay, sure.
I don't know. I mean, think about.
I guess you have to think about you need multiple linear regression if you don't have very complex data.
So let's say you have data, you have the option to use it or not. Do you think it's going to help, or could it give you a worse answer?
Not a straight yes or no answer.
Not a straight yes or no. Another?
Would it be basically depending on like what you're trying to find? So like if you're trying to find how multiple different factors affect something versus if you just want to see this one thing and how it might affect your end results, you don't really need to use it.
Yeah, I think you're saying that maybe we want to do an experiment to see which things are most affecting the target, like which features are most important to predicting. So in that case, we might want to do something like try them one at a time. If I understand.
Sort of.
Yeah. So, but let's say that our goal is simply to get the best prediction we can. That's our only goal. Are we going to do any worse with multiple than Single. Okay, so so at least the answer is, if we're working with the training data and we're measuring performance on the training data, we're never going to do worse with multiple linear regression than single. But there are cases later where, more complex cases where maybe our training set doesn't match the test set we're eventually using, and it could be that we're better off actually using fewer predictors than all of them. And we will get back to those questions in Unit 4. But for now, we're going to just say, I have a training set. My whole goal is to minimize my prediction error on my training set. And in this case, yes, multiple linear regression can be no worse. It's usually better. In the worst case, it's the same. So let's see how this goes. Let's do an experiment with our diabetes demo. So what we're going to do is we're going to make a for loop over the different features, and we're going to use one at a time to predict the target. So we're going to do simple linear regression over and over and over with different features. So that means that for every feature, we have to find the mean of x, that particular feature. We have to find the covariance between x and y. We have to find the variance of x. And then we have all the ingredients. We can find our beta 1, beta 0. We can find our r squared too, because r squared is going to tell us how well that worked. And here what I'm doing is that the for loop is just printing out, like for feature j equals 0, our r squared was 0.035. Is that good or bad? Very bad, right? It's much closer to 0 than it is to 1. So it's very bad. And then we're also printing out the specific beta values, beta 0, beta 1. And we go to the next feature, we find it's even worse, 0.001. Okay, and so on. And if we look through this list, the very best one is 0.34, which is it's not as bad as some of the others, but still it's not getting close to what we had before, 0.51, which is what we get when we use all of them together. Okay, so this is just an example of what tends to happen. Yeah, so our least squares design, it's really figuring out how to extract the most it can from the training data to perform the task of predicting the training targets. So definitely it's going to win. That's what we find here. Okay, but now you could say, well, this is not... Okay, so let me just highlight this just to make sure that we all understand what's going on here. Sorry, there's a typo. It should say in general. In general, least squares linear regression performs at least as well as least squares simple regression. And I'll write here on the training data. Okay, so now to clarify what I mean by training data versus something else, let's think about what might be something that's a bit more realistic. Because in practice, yes, we have some data we're training with, but then we're going to apply our model later on, once it's trained, to some new data that we don't have access to during training time. That we call test data. So that test data, that's really what we want our model to perform well on, right? Who cares if it performs well on the training data if it fails on the test data? So what we really hope is that statistically, the test and training data look the same, so that, if it performs well on average on our training data, it should perform well on average on our test data. That's what you can hope. But in practice, the test and training data will never be the same. So let's do a little experiment here with this diabetes data, where we take our 442 samples total and we split it into two parts. We'll just keep the first 300 samples as our training data, and we'll keep the other 142 separate as test data. And so now we have to redo our model. We're only going to fit our model based on the first 300. And then once that model is fit, you can see that over here. So once that model is fit, we can predict the training targets, but we can also predict the test targets with the same model. And then we can compute r squared separately. And what we find in this case is the results are pretty close. Training gives us an r squared of 0.15 0.47, test 0.5072. So pretty close. That's what you would hope, because we took one big data set, we split it into two. You have to be a little bit careful when you do that split. Generally speaking, you want to randomize your data, make sure it's all shuffled before you split it, because sometimes data sets are ordered in some way. Maybe someone sorted the labels from big to small, and then if you only predicted on the small labels, you might never figure out how to predict well big labels. So when you do this, we didn't actually do any shuffling here. This was just a real simple experiment. But in practice, you always want to do something like shuffling. And we'll talk about that in the next unit. But this is sort of, bringing up some ideas that you can see how the performance on the test set is usually you expect it to be a little bit worse, because it's not what you had to train with. It's a little bit different. So, and this is where you can see sometimes a negative negative R squared on the test data. Maybe if you had like a barely positive R squared on the training, it actually might be negative on the test. Okay. So anyway, this is done in the demo. Any questions so far? Yeah.
If you have your training test split and it's pretty similar, the training and the test accuracy, is there any reason to not, aside from time, go through with all your test data, put back in the training model and train it so you have even more data trained on?
Oh yeah. So I think you're saying split it at first.
Split it first, test the accuracy of the model, then if it's good enough, put the test data back in the training.
Yeah, you're right. That depending on what we're trying to do, that might be good in the end, and we'll definitely talk about that later when we talk a lot more about this stuff in the next unit. But yeah, that is a good idea. But we won't. I don't want to talk about it yet. Any other questions? Yeah.
So, in general, can we say that the more number of features, the better our model?
That is a great question, and that is exactly what we're going to talk about later today. So I'm not going to answer it yet. That's a great question. Okay. So we're going to switch gears for a moment, and we're going to talk about how to deal with what are called categorical variables. So here's an example. Back to the automobile miles per gallon prediction. Let's say I want to predict the miles per gallon of a car given horsepower, X1, brand, X2, where the brand is something like Ford, Honda, BMW. So how do we represent those brands numerically? Because we need numbers at the end of the day, to run our model and everything. So
Just arbitrarily choose 1, 2, or 3, etc. for the brands.
yeah, so that is one thing we can do. Does anybody think that there might be an issue with that? So here I called it, 1, 2, 3 for this brand. Like Ford is 1, Honda's 2, BMW is 3.
I mean, can we get crazy that you can encode them or put them into a vector space so you get a representation?
We could, but do you see does anybody see a problem with this first method?
Yeah, it's gonna perceive let's say you have 10 brands, right? You have
Well, what about these 3?
Okay, yeah.
3 brands.
It's gonna perceive 2 and 3 as more related than 1 and 3.
Could be, or
Increase.
maybe we could even say they're ordered. In this case, it means that Ford is less than Honda, is less than BMW. And in fact, even more, the difference between Ford and Honda is the same as the difference between Honda and BMW, right? You're kind of imposing a structure on the brands that might not actually be there. So you can see why this is very dangerous. You don't want to do this. Definitely don't. So we have to figure out some other way to describe brands. And this idea of embedding them in a feature space is exactly what we're going to do. So this is called one-hot coding. We're going to code brands as binary vectors. So let me be specific what we mean. So here's a little table that shows exactly one possible way of doing it. So we're going to expand this brand, which originally was just a real number, X2. We're actually going to expand that into a vector, into 3 different entries here. X2 soup 1, X2 soup 2, X2 soup 3. And we're going to, depending on the sample, if it's Ford, we're going to set those 3 as 1, 0, 0. If it's Honda, we're going to set them as 010, and if it's BMW, 001. So now you can see that we're not imposing any ordering between Ford, Honda, and BMW, right? They're, like if you wanted to try to plot this in 3 dimensions, it would actually be like you have in 3 dimensions, you have 3 orthogonal vectors. They're just all perpendicular to each other. Okay, so this is a lot safer. But actually, we can understand more precisely what's going on if we just follow through and think about what the model will give us in the end. So in this case, the model we're actually going to fit looks like this. So you can see that we're actually going to have 3 parameters, 3 betas, instead of just 1 beta for brand. We're going to have beta 2, beta 3, beta 4. And of course, as before, we have an intercept, and we have a slope on the horsepower. Okay, everybody with me? So let's go one step further and think, what if a particular sample in the database was a Ford sample? What would happen? So we know in that case that x21 is 1 and the others are 0. So basically, this becomes a 1, the others disappear, and in that case, your model essentially looks like this. You have, your intercept is now beta 0 plus beta 2. On the other hand, what if you had a Honda sample? Well, then these guys go to 0, this goes to 1, and so you actually get effectively this model. And so now your intercept is beta 0 plus beta 3. Okay, and then similarly for the BMW sample, your intercept would be beta 0 plus beta 4. So essentially what you're actually doing when you do this is you're allowing a different intercept for every category. You're not using one intercept fits all. You're allowing each category their own intercept. Okay? So that's really the best way of understanding what's going on here. So there are times when this is a good thing. This is something you want to do. There are other times where, maybe you want to do something a little differently. And let me give you an example on the next page. So here's the example. So suppose, again, we're measuring the miles per gallon of a car, given its horsepower and brand. But what we know is that different brands measure horsepower differently. So let's suppose that these guys at BMW, these Germans, they always like to overinflate their horsepower. So when it's 50, they actually say it's 60. And then maybe, the Japanese at Honda, they're very modest. And so when it's 50, when they say it's 50, it's actually 60. So, maybe we know this, and so we want to calibrate. And so we might say, well, I don't want to think of horsepower the same for these different brands. It's not the slope that I want, it's not my intercept that I want to be brand specific, it's actually my slope. So what you could do is you could still use this one-hot coding. You could set up x2, expand it into this 3-array binary vector. The one-hot coding, if I didn't explain that just means that in all cases, one coefficient is non-zero and the rest are 0. But then you could apply it in a different way. You could apply it this way, where what you do is you actually multiply x1 by that binary vector. So you have an x1 in all cases, but then you get a custom coefficient in front of it, and then you can think of these almost like as switching variables. They're either on or off depending on the brand. When you do things this way, and you look at what's actually happening, if you had a Ford sample, then all this stuff is turned off. The x2 is 1, and you get this model. On the other hand, if you had a Honda sample, then these go away. This one is 1, and you actually get this model. And finally, BMW, you get this model. So now you can see that what you're actually doing is you're allowing yourself a different slope coefficient for every brand, as opposed to using a different intercept coefficient for every brand. So whichever one you want to do, really depends on maybe some side information you have about the data set, about how to interpret it. You could do both. You could do one-hot coding slope and intercept. And in this case, essentially what that would mean is that you use specific coefficients slope and intercept for every brand. So, that may or may not be a good idea. The more coefficients you add to your model, it's not necessarily better, as we'll see. It gives you more flexibility, but sometimes that flexibility, sometimes you can have too much flexibility and it actually hurts your prediction. So we'll see some examples of that later. Anyway, is this idea clear, that how you do the one-hot coding? So this is what you always want to do whenever you have a feature that is not an ordinal number. So these things are either going to be ordinal, which means they're ordered, or categorical, which means they're categories that should not be ordered. Let me give you another example. What if I have an Amazon rating that's either 1 star, 2 star, 3 star, 4 star, 5 star? So there's 5 possibilities only, so it's discrete. Is that ordinal or categorical? Someone said categorical. How many people think it's categorical? How many people think it's ordinal? Okay.
Could you say this?
Could I say it again? Okay, so I have Amazon. I have a rating between 1 and 5 stars. So that's my data set. It's like, it just tells me my rating. It's an integer, 1, 2, 3, 4, 5. Is that should I treat it as an ordinal feature or should I treat it as categorical? That's the question. So the answer is there is a clear ordering. 1 stars is less than 2, which is less than 3, less than 4, less than 5. So I would say that's definitely ordinal. Just because it's discrete, there's only 5 possibilities, does not mean that it's a categorical quantity. It's definitely an ordinal quantity. Categorical is more like dogs, cats, cows. It's like you can't really order them. They're just categories. Treat those as categories. So there will be some, so you might have some homework problems and stuff where you can think about, how to think about these categories and so on. Okay, are there any other questions? Yes.
What if we have too many categories that we end up with too many parameters?
It's true that so there is this parameter explosion. I think this is just probably the only way to do it that I know. So you end up getting a lot more features, hopefully you have enough data that you can leverage it. Okay, great. So let me point out one other issue. Let's come back over here and look at this. So you might notice that there's a certain redundancy here, right? When you look at our intercepts, there's 3 intercept quantities, but there's 4 variables that I'm using to describe the intercept: beta 0, 2, 3, 4. So there's sort of a redundancy, right? Like I could do fine without the beta zeros. So this actually leads to problems if you're not careful. So let's see what happens. It turns out that this, if you remember, there was a certain matrix, A transpose A, that we said should be invertible, otherwise we didn't know how to do the least squares fitting. It turns out that matrix actually loses invertibility if you use that redundant one-hot coding. So let's see why that is. So this is back to the model, the one-hot coding of the intercept that we saw a couple pages ago. So as you can see in this case, we're going to have a total of 5 beta coefficients. And when you look at the rows of our A matrix, they will have one of 3 forms. They'll either look like this, or this. So all the Ford samples will look like this, all the Hondas like this, and all the BMWs like this. So here's the weird thing, is that I can come up with this special beta vector, this one in particular. And if you look at this, if I apply that beta vector to this data, it will result in predictions that are always 0. Because this times this column vector, you get this times this, that gives you a -1 always. This times this gives you 0 always. This times this gives you a 1 always, or you get the 1 here, or you get the 1 here, and then the other ones are 0. So no matter what happens, you multiply this beta times your A, you always get 0. So if that's the case, that means you have this relationship going on, right? And if that holds true, that means I can multiply both sides of that equation by A transpose, and I get this, that holds true. And now if you think back to your linear algebra and you say, I have a matrix, in this case it's A transpose A, such that there's a non-zero beta vector, such that when I multiply that matrix by it, I always get a 0. You know that this matrix is not invertible. It's what we call singular, not invertible. There's no way, in particular, like if this is going on, I have no way of finding out what beta is, right? Because this matrix just killed beta. It just set it to 0. I can't go back. Okay, so this is a case where I can't invert this matrix, and I would, depending on how you implemented that model, like if you use that A transpose A inverse method, you would find you just get an error. Python would say, like, sorry, I can't invert this. So there's a couple ways around this problem. One way is just to be a little bit smarter with how you do the one-hot coding and say, I'll just use a simpler one-hot coding scheme where I only expand it into 2 binary vectors. And so, for example, you could use Ford as 1, 0, Honda 0, 1, and BMW as 0, 0. And if you do this, that's essentially saying that that last column is always 0, which would mean in this case, it would basically get rid of this beta 4. You never have that. And this is all the freedom you need. So now beta 0 is the BMW intercept. And no matter what beta 0 is, beta 2 and beta 3 give you the flexibility in the Ford and Honda intercepts. And there's no redundancy. So this would cure the problem. There's another way of curing the problem, which we'll talk about in Unit 4, which is to use what's called regularization, like L2 regularization or something. And that's another way to protect against situations where the data you're given is just not invertible. There's just no way of making it, there's no way of making this invertible. And so you have to do something to deal with this. So we're going to talk about that a little bit later. All right. Any questions on this? Yeah.
Is there one of those that's like yields better results for your predictions? Mixing it?
Yeah. I think for now this is the best because this is simple. It's very clear how to do it. You have a simpler model, less parameters. That would be the clear winner. This has problems. There's sort of a bias issue. Like it actually moves you a little bit away from what you would like to do. So it makes it solvable, but there's a slight cost. So for now, yeah, this would be the preferred thing. This does not happen, by the way, when you're one-hot coding the slope. It's specific to one-hot coding the intercept. Okay. And so the last thing we'll talk about, last slide of this unit, is what if I am not content with linear regression and I want to be more clever? I want to do, let's say, polynomial regression. So here's just a few pictures of, this would be simple polynomial regression. So we have a single scalar feature x, scalar target y, and I just want to come up with a curve that maps x to y. So here you can see if the data are these purple dots, it looks like this 9th order polynomial would be a really good choice to do the modeling, better than a linear model or even a 3rd or 5th order, right? So this is something that's pretty reasonable to do, pretty reasonable to want to do. And so it turns out that you guys have all the tools you need to solve this. All you have to do is come up with features that make our problem look like a multiple linear regression problem. So all you have to do is you take your scalar feature x, you raise it to the jth power, where j goes from 1 through d being the maximum order you want, and you set that, x to the power j as x sub j, which is the data you use in your model. So this is like x sub 1, x sub 2, x sub d, and at that point, you just have a multiple linear regression problem. Does that make sense? So all the tools that you guys have learned, you can actually do something much more powerful than linear regression now that you have them. You can warp your data, x, as much as you want. You can make all kinds of different warpings of it, make it really complicated, and then you just have a much larger linear regression model. And there's plenty else you could do. Like the polynomial is just one example. Maybe I want to do like cosine, where I use different frequencies. there's just tons of different options once you realize you can pre-process your data. Okay, so is this idea pretty clear? Question?
I mean, knowing which transformation to use, that's like having some outside knowledge.
Knowing which transformation to use is critical. That's a great point. So, so if you have that outside knowledge, if an expert tells you, you can do it. What we will aspire to do as we get deeper into the course is we will aspire to learn that transformation. And that is essentially when you do have like a deep neural network, you can think of the last layer as just a linear layer, and all the other layers are learning an optimum transformation that fits your data the best. So yeah, this linear stuff, it seems really weak and simple, but actually, when you combine it with pre-processing, it can be as powerful as you want. Okay. So now let's pause for a second and ask, what do we mean by linear regression then? Where is the linearity? Do we need our model to be linear in the features or linear in the coefficients or both? What do you think? And what I mean by linear graphically would be like things move in a straight line. If I vary one thing, the other thing moves, as a line. So what do you think? Is it important to be linear in the feature X in this case? To actually carry out the procedure of linear regression? No. Here you can see this term is linear in X, but these terms are nonlinear in X. So the linearity that we need to do all the stuff we've done is not in the X's, it's in the betas. So Y is linear in each of the betas, right? If I froze everything and plotted Y versus beta 0, it would just be a straight line with slope 1. If I froze everything and plotted Y, everything except beta 1 and plotted Y versus beta 1, it would be linear with whatever value X is. So the point is that the linearity, when we talk about linear regression, it really needs to be linear in the betas. If all of a sudden I change this and I put a square on one of the betas, all the derivations we did go out the window. You have to start over and figure out how to optimize that model, and it's going to be different. So when we talk about linear regression, we're really talking about linear in the parameters. So that's just one point I want to make. Okay, great. Any other questions? Okay, so the kind of leading question for the next unit, which is related to some of the questions that you guys asked, is how do I know, if I want to do this, how do I know what the right polynomial order is if I didn't have an expert already tell me? A related question was, is higher order better? Is that just, I should just go for the highest order I can handle? So that's essentially the main question we're asking in the next unit, which is about model order selection. And we'll see it kind of comes down to this thing called the bias variance trade-off, which is a way of understanding the answer to that question. So we're going to come right back to this polynomial model that we just talked about. So in this case, I'll just write it again. So y is going to be beta 0 plus beta 1 times x plus beta 2 times x squared and ... all the way to beta sub d x to the power d. So in this case, we have d plus 1 model parameters. We put them together in our beta vector. We know how to solve this problem. That's not the issue. The issue is, how do we select d? Can we select it from the data itself? That would be our goal. Sometimes an expert tells us what it is, but often we just don't know. So we want to figure that out ourselves. And this is an example of model order selection. And basically, it's an example of how complex do you want your model to be? Do you want your model to be more and more and more complex, less and less? Or is there some sort of Goldilocks in the middle setting where it's just as complex as you want, not too little, not too much? So what we can do is like how every one of these units has a data set. Well, in this case, the data set is going to be synthetic. We're just going to create our own data. And sometimes this is a really powerful thing. If your goal is to if you're making a new model or inventing some new machine learning tool, you understand how it works. And so by making your own data set and maybe changing your data and seeing what happens, you can get a sense for how your model is working. how it behaves as the data changes. So that's what we're going to do. We're going to use synthetic data, and we're going to construct our data as follows. So this is, again, simple regression in the sense that we start with a single scalar feature x, and we're going to just choose random values of x uniformly distributed between -1 and 1. For each of those x, we're going to assume that there's this underlying true model, which is given by that red curve. It turns out that this is a polynomial model of order 3, cubic. But of course, it would be too simple if we made our data sit exactly on that line. So we're going to add a lot of noise to our data, and our data set's going to be these blue dots. And as you can see, the dots are big enough that it's not exactly obvious what the best model is. At least, maybe just looking at it. So there are definitely techniques that we'll learn about to figure out what the best model is, but maybe it's noisy enough that it's not obvious. Okay, so in this case, just for some notation, we're going to write our model. We're going to write yi as some function f of xi plus a noise that we're going to call epsilon I. So in this case, this is like the underlying noiseless true model, and that's the red curve. And there's, of course, some true coefficients. There's 4 betas that are the true ones, and you can see in this little code snippet here, the true coefficients are like 1.502. Okay, so this is just the data we're making, so we can play with these ideas. There's a nice polynomial package in NumPy, which we're going to use quite a bit in this section. So we're going to import that and call it poly. And as you can see, like the polyval command is a way if you have a vector of these x's and your betas, then it can generate all these samples. So we use polyval to do that. Another thing, maybe this is the first time we're seeing it, is how to create random quantities. So like this is normally distributed random numbers. That's how we get the noise vertically, and uniformly distributed is how we get our samples x. So we can do that with the NumPy random package. Okay, so so let's see what happens first if maybe we guess, or maybe someone tells us that the model order is 3, the true model order. So as we learned earlier today, we could use the sklearn linear regression package to do our linear model fit. That's fine. But just because we're working with this polynomial package, it turns out that it also has a least squares polynomial fitting package that will give the exact same answer, and it's called polyfit, and we're just going to use that. So you give it your x data, your y data, you give it the polynomial order, and it will fit order 3 polynomial. And here it returns the coefficients directly. So that's what we're going to do. And it turns out for this data set, when we do this, and then we're going to print the curve that we learned, it's the green one, you can see it's really pretty good. It's almost identical to the truth. So even though there's all this noise, this least squares fit that found out how to adjust those 4 coefficients to minimize the sum squared noise prediction errors, it actually worked out really well. Okay, so that's if we knew the true model order. What happens if we got the model order wrong? Okay, so this is what happens if we assume a linear model or a polynomial with order 1. So that's the green line we get. This is the least squares fit. As you can see, it doesn't really come close to the truth. If you step back and just look at the blue dots, you can say, well, it's not a terrible approximation of the blue dots, but yeah, we're kind of missing some blue dots over here and here that give us the indication that maybe we could do better. So that's what we call underfitting, is when you use a model that is too weak relative to the truth. You can go the other way. What if we tried d equals 15, 15th order polynomial? This is a model that's way more complex than our true data is. And this is what happens. You get this green curve over here, and you can see that it's kind of has some weird squiggles in it. It's learning to put some weird curves in there. And then it's also doing something kind of crazy at the edges. And so there's a question, well, which one is better? Because someone told us the truth, they told us what the truth is, you can obviously see that neither of them is a perfect fit. But let's say you didn't know the truth. What's kind of another issue that arises with this overfit model? What kind of problems would this stuff cause? Can you imagine a situation where that'd be really bad to have those?
Asymptotes.
Can you say it again?
They kind of look like asymptotes.
No?
If you had anything just slightly above or slightly below what your training data was,
Yes.
way off.
Exactly. So if your test data is out here, it's going to be way off. So there's no big problem with your training data, but your test data, you get a terrible result. So that's this danger of overfitting, is that, or even over here, like if your test data is around this point, you can see you're going to be predicting something, far from what you should be. So in some cases, there's actually no problem at all. But in other cases, there's a huge problem. Okay, so here's another illustration. It's just hand-drawn, but it gives the same idea. Underfitting, the true model in this case would be something like this. Good fit would be like this, and then an overfitted model. If your model is, if it's complex enough, you could even go through all your training points perfectly, get 0 prediction error. But is that what you want? Right? Maybe not. Because what are you fitting here? Are you fitting the trend, the true trend of the model, or are you fitting the noise in the model? Here, I think we're fitting a lot of the noise, right? So that's not what we want, because at test time, I'm maybe going to have a sample that's over here. That would be typical of my data, and you can see I'm going to be very far off from it. Whereas if I had this one instead, I'm going to be much closer. Okay, so this is people call this underfitting, overfitting, and then we hope to be in between. Okay, so the question now is, how do I figure out, what's a good scheme for figuring out the best model order? So here's just an idea. What if we do this? What if I hypothesize each different model order? I start at 0, then 1, then 2, and I run an experiment where I fit the model, and I print out the error on the training data. Is that going to be a good approach? What's going to happen?
Well, if you overfit it, you're going to get a good number.
Exactly. So this is kind of the trend that we see. This is just an experiment where we try each of these model orders, 1, 2, 3, 4, in turn. We're plotting the mean squared error. We could have also plotted RSS. Here we're just plotting the mean squared error, which is we could have plotted R squared. Here, this is the RSS divided by the number of data samples. So it's just scaled RSS. And as you can see, as the model gets more complex, more polynomial coefficients are allowed, the training error just gets lower and lower and lower and lower. And in fact, if you took this out, further and further and further, and if your optimizer was really able to fit that polynomial, which is not an easy thing to do, you would eventually get to this point where you would find a polynomial that passes through every one of your training points perfectly, and you would drive this all the way to 0, and that's the lowest you can be. Okay, so this is not a good approach. This leads to overfitting. This basically will always tell you to use the most complex model you tested, because that will give you the largest or the smallest training error. Okay, so that's not what we want to do. So you might say, well, is there a way I can explain what's going on? So one way you can think about this is just to think about how the models relate to each other as you change the model order. So we can think of it this way. When you have a model order of 1, you're fitting beta 0 and beta 1 only, which is kind of like, maybe it's sort of like if you have a beta with 15 values, but you force all of these ones to be 0. And then when you increase the model order, it means This next one, you're not forcing to be 0. You're allowing it to have more freedom. And then the next time, you're allowing this next one. So you have more and more freedom every time. The model is more and more capable. And so there's no way that it could do worse. If I have a model that's better, and my objective is minimize training error, that's what I measure, that's what I designed to do, that's what I measure, there's no way I'm going to get worse. It's just going to get better and better and better. So that's kind of one way to think about why this is failing. To answer the question from the last unit, more is not always better. It's better for the training, but once you think about what's going to happen with a test set that's different from training, it's not necessarily better. It could be a lot worse. And if you have a linear model, so this is what we've been focusing on in Unit 2, Unit 1, you can see exactly when you're going to get 0. So as you have, so let's say I fix the number of samples in my training data set. So I'm fixing this dimension, but now I'm allowing the number of features to grow. That means I'm making A wider and wider. Once I get to the point where A is a square matrix, let's just assume that it's full rank and invertible. I can invert it, and all of a sudden, I drive this to 0, right? So at that point, I get 0 error, and anything more than that, I can never get smaller error. Then I've perfectly fit all my data. But really, I'm overfitting. I'm just fitting the noise. Okay, so that's not what we want to do. We don't want to fit the noise. We want to fit really the trend of the underlying data before the noise was added. And so that's this challenging problem, and that's what this whole unit is all about, how to do that. Okay, any questions so far? Yeah.
When you try to, when you clean your data, when you try to filter out the noise before training? Or?
Yeah, unfortunately, that's really hard to do. So, if I just gave you those bunch of dots, right? It's like, how would you clean them? In some sense, that's what we're trying to do. We're trying to find this clean function. That's our whole objective. That we're fitting that model. And so, yeah, how do we do that? That's our whole objective. Okay, so, all right. So, so we're the approach we're going to use is we're going to split the data we're given into 2 parts. One part we're going to use to train our model. The other part we're going to use to evaluate our fit. And what you do, what you see when you do this, is that the blue curve is what we saw a few slides ago. That is the mean squared error on the training data. That's the one that just gets better and better as the model error increases. But when you look at the performance on the test data, you can see, yes, it initially decreases a lot, but then it gets to a minimum and then it starts to increase. So, this is kind of a step in the right direction. It's not, as you can see, it's not giving us 3. 3 is the order we really want, right? It looks like in this case it's minimizing, it's bottoming out around 6. So this method would tell us to select 6. So we actually are going to improve upon this, but this is sort of the big conceptual idea is split your data into a training set and a testing set. And in the testing set, you're going to evaluate your model order selection. This is not going to be the final test set, which is something that you don't even have access to during the design process. That's something you'll see, much later. This test set, sometimes people call it validation data, sometimes they call it test data. It's not a consistent usage, but it's something we're using for design, but something we're specifically not using during training, if that makes sense. Okay, so, but I think this is a good place to stop. Are there any questions on anything so far? All right, have a great weekend. See you guys next week. And of course, Monday is off, so we'll see you next Wednesday.